understanding of polymer statics, I have the lovely privilege of introducing you to Polymer Dynamics. So we think about simple geometries to measure things, and the simplest one is what we call simple shear. And in this slide, I can define what I mean by shear stress, which is force divided by the area of the plates that are horizontal in this case, and green. The shear strain, which is the displacement divided by the gap, h. And that lets us immediately introduce Hooke's law, which is that the shear modulus, G, is the ratio of the shear stress and the shear strain. And with the same experimental setup, we could, instead of a solid, put in a simple liquid, which is called a Newtonian liquid because it obeys Newton's law of viscosity, shown in red here. That has to introduce the shear rate. So for the liquid, if we apply a constant force to the top plate, it's going to move with a constant velocity. And that generates a constant shear rate in the liquid between the two plates. And then we have Newton's law of viscosity, which is the viscosity is the shear stress divided by the shear rate. And since we use shear rate so much, I'm going to use the notation gamma with a dot on the top for the shear rate. Okay, so the first simple model of viscoelasticity, where we combine elastic character and viscous character, is known as the Maxwell Model, the same James Clerk Maxwell who's famous for all sorts of things in physics. And the way to think about it is that we have an elastic element and a viscous element in series, and this classic thing is shown on the left, but I kind of like this one in the middle, where I think of two parallel plate rheometers. One has a Newtonian liquid and one has a Hookean solid, and they're in series with each other. So series means the strains of the two elements are going to add together to get the total strain, and the stress in each of the elements has to be the same. And so that's exemplified in the first two lines. So the stress is the same. It means the stress is the Maxwell's modulus times the strain in the elastic element, and it's also equal to the Maxwell viscosity times the shear rate in the viscous element. We can, well, so that those introduce G and eta again, but they have the same meaning that they did for the pure elastic material and the pure viscous material. And then there's a natural relaxation in time in this Maxwell model that is basically the ratio of these two parameters. So viscosity always has units of Pascal seconds, and modulus has units of Pascal, so this relaxation time has units of seconds. And what we first imagined doing is a simple step strain experiment. So we instantaneously move the top plate, and we hold it there for all time, and we watch the stress, and the stress is going to decay with time. And by studying that stress decay more generally, we can learn about the viscoelasticity of the material. For the Maxwell material, that decay is particularly simple. It's going to work out to just be a single exponential. So this lets us define a generalization of Hooke's law, which is called the stress relaxation modulus. It's going to be time-dependent because the stress is decaying in a time-dependent way. And of course, the strains add in the two elements, and the stresses are the same. And so we can combine those two equations to get a simple differential equation shown on the right here. I go kind of fast because I think this is review for 80% of the people in the room. We get a simple homogeneous differential equation that we can integrate. We need one boundary condition, which is actually initial condition, that the viscous element cannot deform instantaneously. So it has no response at time equals to 0. And that leads us to a very simple equation at the bottom for the strain in the elastic element, which is, of course, the total strain minus the strain in the viscous element, right? It's a simple exponential decay in time. If we're interested in the stress, this is kind of the simple form that we want, because we want the strain in the elastic element, and we're going to multiply that by the Maxwell modulus to get the time-dependent stress. So obviously the time-dependent stress is then also going to decay exponentially in time. That's the middle equation. And if we divide by the strain, we get the stress relaxation modulus G of T. That also decays exponentially. For a viscoelastic liquid, the stress decays to zero eventually, right? That's true in general. So even if we have a more interesting material than the simple Maxwell material, if it's a liquid, the stress always decays to zero. But you can see for the solid, the stress did not decay to zero. It decays to a final value well beyond the longest relaxation time, which in this model only has one relaxation time, tau m, and it decays to a finite value. And this is, in fact, how we can tell the difference between liquids and solids in our rheometer, right? Whether the stress decays to zero at long times or not. And all we do for a Maxwell model of a viscoelastic solid is just add a constant to G of T, this GEQ, and we get a nice description maybe for something. Okay. So real viscoelastic materials like polymer liquids, for instance, and particularly polydispersed polymer liquids, aren't going to be very close to the Maxwell model at all. But we can always describe them with what's called a generalized Maxwell model. And many of the rheometers actually will set this up for you so that you can model your system. And typically, you never need more than 4 or 5 Maxwell elements if you choose your relaxation times in the appropriate range. And so it's a fairly powerful fitting function if that's what you're interested in doing. And then, of course, once you have a good model, even if it's just phenomenological of G of T, you can calculate lots of things from that. Okay, so then one property is there's always one longest time in any viscoelastic liquid. It might be quite long in practice. You know, I've had materials in my rheometer where the longest relaxation time is a week, and it means I have to do, 2 or 3 week experiments sort of thing, right? But still, it could be measurable. And the way we measure it, the easy way to measure it, is we take the logarithm of G of T, and that's going to be linear in time, right? And so the slope is the reciprocal, well, minus the reciprocal of the relaxation time. So that's a good way to evaluate that. And are some nice data, actually from my 1985 PhD thesis on polybutadiene, a nice monodispersed material. So it's very easy to get this longest relaxation time, and this works out to be 80 seconds for this particular material. I have to say, if you try this with any commercial polymer that's polydispersed, or even worse, has long chain branching in it and whatnot, it'll never quite look linear. And you try to go to longer and longer times, and all you learn is it's never quite linear. So it's not an easy recipe to apply to many things, but for monodispersed polymers, and either in melts or solutions, it works very nicely. Then we next need a simple concept that only applies for linear viscoelastic response. Yes?
For the 20% of the people who don't know viscoelasticity, what exactly do you do in a rheometer? Do you have something and you just push it, it gets stressed, and then the stress relaxes?
Okay, yeah, no, that's a great question. So operationally, our rheometers, because this, particularly if you want to do steady shear, eventually the plates will be miles apart and it doesn't make any sense anymore, right? So instead of doing it like this, we do it in rotation. So we have circular plates and we apply a twist to one of the plates and measure the torque on the other plate. Yeah. So that's operationally how we manage it, typically. Right, so for linear viscoelastic response only, we have this idea of Boltzmann superposition, and actually it applies to all sorts of linear responses in physics, right? The basic idea is that if we had a sequence of small enough strains that are all linear steps, that we could add the responses as though each response was independent of all of the other steps, right? And so each step kind of does its own stress relaxation, and then you just get a sum of all these things where, T minus Ti is the elapsed time since that particular I deformation was applied. And there's kind of a continuous version of that. So if we have any smooth strain history, we can replace the sum with an integral. We integrate back to minus infinity, which is reminding us that any prior deformation has to be accounted for, right? And we integrate up to time t of this g of t minus t prime. Now t prime is the elapsed time since we applied a shear rate at t prime. Let's see, so each one is going to decay in exactly the same sort of form as the Maxwell model, but each with a different elapsed time. And so we can do a simple calculation, which is simple steady shear flow. Here shown like this, but in reality we're doing a twist so that we don't run into this crisis of the top plate being way over here with me. But it's a simple steady shear flow. The velocity profiles are shown there. The shear rate is the way that velocity changes with position, and that's constant through the whole sample in this simple geometry. And so what it means is I can pull the shear rate out of my integral. It's just constant at all times. We can, again, integrate g of t minus t prime dt prime. Well, how do we do that? We have to do a variable substitution so that s is t minus t prime. It means ds is minus dt prime. And change the two limits. At t prime equal to minus infinity, s is equal to infinity. And at t prime, I don't seem to have the other one. At t prime equals to t, s is equal to 0, right? So, so that's at the end. And then what I do is I kill the minus sign of this transformation by switching the orders of integration, and you just wind up with gamma dot integral from 0 to infinity of g of s ds, which, who cares about s? We might as well go back to t, and we get just integral over all time of g of t. So we integrate the entire stress relaxation modulus, we get the zero shear viscosity. So that wasn't really obvious at the beginning, right? That if we just watch the stress decay, we can actually get the zero shear viscosity from that. So that's kind of a simple example of how to use Boltzmann superposition. Now in rheology, we oftentimes plot things log-log, and it drives students crazy. But there's a reason for it, and so these data are kind of exemplary. So if I plot my monodispersed polybutadiene data at room temperature, and remember TG was minus 99 degrees, so we're way above the glass transition, the stress relaxation modulus, we can see the rubbery plateau at short times, right? And then, of course, we watch the stress decay as far as we can go. We can't go all the way to 0. We can never measure all the way to 0. But if we... So the log-log plot's a great way to see the plateau modulus, right? It's that flat part at the beginning of the experiment. But if we take the same data and I plot them on linear scales, this is exactly what we want to integrate to get the stress under the area under this curve is the viscosity. And so this is the way to evaluate the zero shear viscosity from the same data. So both, the good news is both of those plots are useful. And in fact, I think we even did it with log G versus T on a linear scale, and that one would give us our longest relaxation time. And that would actually work fine with these data. The one I showed you is a slightly different sample, I think. Okay, so two related experiments that are very important in rheology for characterizing viscoelasticity are the startup of steady shear, and then once we get to steady state in that experiment, we shut the motor off and watch the stress decay. That's called the cessation of steady shear. The two are kind of coupled, as we'll see here. So this one, in this one, we start with a fully relaxed sample, and at time equals 0, we start shearing it, right? We just start moving the top plate at a constant velocity. And that gives a constant shear rate in our sample. And it lets us define what's called a stress growth coefficient, eta plus. It's time dependent. The shear stress is going to build up with time. Eventually, it's going to level off to the steady state value. And when it does, then that's a real viscosity. But this eta plus just has units of viscosity, kind of a time-dependent viscosity in this startup. And we do the same. So we can use Boltzmann superposition to get the shear stress in this experiment. It's again very convenient because the shear rate is constant, and I can pull the shear rate out of the integral. And in fact, I can start at time equals 0 because I started with a fully relaxed sample. But then I still have to deal with this t minus t prime, and it's exactly the same variable substitution, so I don't want to dwell on that. And we get back to g of s ds as our integral, which we may as well use t instead of s. And so it's like the zero shear viscosity integral, but it's only part of it. It's only from 0 to t, not 0 to infinity, right? So it's a piece of that full integral. And the data looks something like this. So these are beautiful data from Edgar Menendez, who was a student in Gressley's group before I was a student in Gressley's group. For linear response, this is the one at the top. The stress builds up and levels off. No overshoot for linear response. And two different shear rates have the same eta plus. That tells us it's linear response, right? And then as we increase the shear rate more and more, we start to see an overshoot in the stress, and we eventually get a nice flat eta plus. And so these are very nice data, and we can use that flat part to say that's the real steady state viscosity at each of those shear rates, and then I can plot that steady state viscosity as a function of shear rate. So a word of warning: it's important to do this experiment if I want to believe these data. So as the editor of the Journal of Rheology for the past 10 years, I can tell you there's lots of people that want to publish these data, and I say, no, I want to see these data first, because the default of the rheometer is I'm going to shear for 10 seconds, and then I'm going to signal average for 10 seconds. So I ignore the first 10 seconds, which is hopefully all this wiggle, the rise and the fall and all that. And you can see that would work fine for this sample. But other samples can have much longer relaxation times, so you have to be very careful. Otherwise, the value, the rheometer will continue spitting out numbers, but the numbers may not mean what you think they mean. Okay, so then after we reach steady state, we can just stop shearing. That's easy. You just stop turning the motor or stop moving the plate and watch the stress decay, just like we were watching the stress decay from the instantaneous jump, the step strain. And here we define a stress decay coefficient, eta minus. That's that time-dependent stress divided by the initial applied shear rate. Of course, in this experiment, the shear rate is 0. We don't divide by 0. We divide by the initial applied shear rate. And we can, again, do Boltzmann superposition, at least in linear response, right? Same trick. The shear rate was constant. So we can pull that out, but that's only going to be the integral from minus infinity to 0, right? In other words, it's 0 is defined in this experiment as the time when I started cessation. Beyond 0, the shear rate was 0, and this whole integral is 0, right? So we're only integrating during our startup experiment. And you do exactly the same variable substitution again, and you wind up concluding that now I have again the same integral, but here from t to infinity. So eta plus was from 0 to t, and eta minus is from t to infinity. So they're kind of exploring two different pieces of this of the full G of t, if you will. And so here are the eta minus data. In linear viscoelasticity, the stress decays rather slowly. As I apply larger and larger shear rates, what happens? I start stretching chains, right? And the chains are kind of stretching and retracting. That's what the dissipation that leads to shear thinning is all about. And as I go to higher and higher rates, when I stop, I catch more chains on average in a more stretched state, and the stress decays faster. So that's kind of an important viscoelastic experiment that unfortunately not so many people use, but it's a really useful one. And then we can think about our two integrations. They're basically two pieces of the full integration to get the zero shear viscosity. The stress growth up to a certain same time t is the blue integration, and the stress decay that started at t and went to infinity is the red part. So yes.
So in an experiment, you control gamma prime, and what is the primary thing you're measuring? G?
No, we're measuring stress. Yeah. So we're in both experiments, both the startup and the cessation, the shear rate is controlled, right? In the startup, it's a constant shear rate. In the cessation, the shear rate's 0. And we're watching the stress in both cases. And so we measure the time-dependent stress, say, in this decay experiment. We divide by the initial shear rate to get this, what I call eta minus. Yeah?
And then you invert that to get a G. How do you get the G?
We would have to measure the G of t, I guess, in a different experiment if we want to make this comparison. But yeah, this is just kind of a construction that the eta plus is the early part up to time t, and then the decay is covering the later part effectively. So the point is, in linear viscoelasticity, all these guys are kind of connected, but the problem is the Boltzmann superposition only applies to linear viscoelasticity. It only tells us about the zero shear viscosity. And so what's not shown here is I could have data that go all the way over here. It'd be nice and flat, right? That's all linear response. If I double the shear rate, I'm going to double the stress, and I'm going to get the same viscosity, right? So that's linear response. All these lovely nonlinear shear thinning data don't. The Boltzmann superposition principle doesn't apply to anymore, right? So, and then you might wonder, well, why is there this big gap, and why, indeed, and the problem is, the typical way rheologists like to do steady shear in their rotational rheometer is to use the cone and plate geometry. It happens to have a uniform shear rate everywhere in the sample, but unfortunately, with polymer melts, at least, that is very limited. It's almost as soon as we get into the shear thinning regime, we no longer can do the experiment, because you'll see that the data start going down like this. As soon as they start going down steeper than a slope of -1, you know something's wrong, and then you look at your sample, you use your eyes, the most important instrument in the lab, and you see, oh my gosh, this perimeter of the sample looks terrible, and half the sample's not even in the gap anymore, right? So you say, well, I can't believe those data. And so then we turn to some sort of Poiseuille flow, capillary or a slit rheometer, to get these high shear rate data. Historically, there's always been this gap here, but Professor Vlasopoulos is going to tell you how you fill in the gap with a fancy thing called the cone partition plate that allows you to get a little bit of that edge fracture without affecting the data you're trying to measure yet. Okay, any questions so far? Yes?
So when you shear like this between two plates, every point in the material will experience different shear strain rate. How could you determine the exact strain rate?
Well, the assumption is that if the top plate is moving at a constant velocity, every element in between the two parallel plates is at the same shear rate. There are cases when that might be violated, but all of this is assuming it's at the same shear rate.
The question is, how many plates is parallel?
Oh, cone and plate.
No, he's asking about parallel plate wasn't uniform. So
So
Okay, so yeah, so these data are from cone and plate geometry where the shear rate is everywhere the same except right in the truncation gap, right? I don't know, why is it going to help? Whereas I think you're thinking about parallel plate, right? And this one, of course, we don't use this to get the shear rate dependence of viscosity. It's okay for what we're going to talk about next, which is oscillatory shear, but not for steady shear. Yes? Yep. Yep. Yeah, and the key point is, T is a little bit interesting, right? Because I can watch that that stress buildup, for instance, this one, and go out to longer times. If I go out to longer times, then the blue is going to go out all the way out to here, and only this part will be red, right? No. So all of these data are actually the G of T of the step strain experiment, right? And now we're doing this construction to kind of show which pieces of it belong to stress growth and which belong to stress decay. And the key point is as T gets longer in those two experiments, the stress decay has decayed to zero and the stress growth has reached its final value or is approaching, yeah? Yeah? Yes. In each experiment, right. Yep.
So different behavior of the cessation, what does that tell us about?
Okay, that's a great question. So I only mentioned that briefly, but as we go to higher and higher shear rates, it decays faster. And we're effectively catching the material in a more stretched, each chain on average in a more stretched state. Those stretched states can relax rapidly by what's called Rouse retraction. They can relax stress faster, or they don't have to rely on reptation, which is slower, right? So as we go to higher and higher rates, it decays faster. It's telling us information about how stretched the polymer chains are. Yes?
It might have been asked before, but I don't hear the question saying front. The T, what's dictating what the T is? Because I can imagine that the stress growth and the stress decay is very much dependent on how you choose your T.
Oh, absolutely. And so for any T that I want that's the same T in the stress growth and the stress decay, I can make this sort of a construction, but it might move over here or it might move over here, right?
So is it clear to choose as an experimentalist, or is there...
Well, yeah, no, it is. It doesn't have it to do with the experiment, really. It's just showing that this integral plus this integral gives us this integral at any T you choose. Yeah. Yes?
And this is like this plot is just for shear rate which are in linear.
That's right. It should be the corresponding to the linear response, which is just this top curve, right? Good. That's a very good question. Yeah, it only works for linear response. Okay, so the thing everyone does is oscillatory shear. The reason is really simple, because I can have the technician in industry that barely graduated from high school measure this, and we can believe the data, right? This is really the main reason this is the most popular experiment. It's kind of foolproof. So what we do is we apply a sinusoidal strain, a sine wave, like shown at the bottom, and there's only two parameters. There's an amplitude of the strain wave, and there's a frequency, omega. So the nice thing about oscillatory shear is I get to choose omega, and I get to probe the linear viscoelastic response on the time scale that's 1 over omega, right? So it's kind of directly. And let's see. The shear rate is, of course, the time derivative of the strain, and that's cosine omega t, right? So it oscillates 90 degrees out of phase with the strain. That's important. And the stress is generally going to be sinusoidal with the same frequency, but have a phase lag, delta. The stress actually, you can see in the bottom, in the heavy, is actually leading the strain by phase angle delta. We can think about two simple limits of that. But it's very important to realize that the rheometer does not measure G prime and G double prime, which we'll get to. It measures the magnitude of the complex modulus, which is the ratio of the amplitudes of the stress and strain waves. And it measures the phase angle, the amount that the stress leads the strain, basically. Those are the two things it measures, and it calculates everything else. So sometimes it's important to know what my rheometer actually measures. So if we have a simple Hookean solid, of course it obeys Hooke's law. Stress is modulus times strain at any time. And so that material is going to oscillate perfectly in phase with the strain, sine omega t, shown as, the peaks and valleys are corresponding to one another. And what does it do? It measures the shear modulus. So the magnitude of the complex modulus in this case is just the shear modulus. Whereas if we deal with the Newtonian liquid, what happens? The Newtonian liquid doesn't care about strain. It cares about strain rate. And so we need the time derivative of the strain, which is cosine, and that's going to oscillate exactly pi over 2 out of phase. So in the first one of the the Hookean solid, delta is 0. In this case, delta is pi over 2. And more generally, delta can be have any value between 0 and pi over 2. So it's telling us how viscous versus elastic the material is. The larger the phase angle gets, the more dissipation there is. And so this one shows it for kind of a general case. Again, the stress always leads the strain. In other words, it has its peak before the strain has its peak. And now we can get to defining storage and loss modulus, which are the nice things as a function of frequency that the rheometer just spits out. But and though we consider those to be our data. So one part of we have a general stress wave, right, with the same frequency as our strain. That's important, but with a phase lag. We can always separate that into two orthogonal parts. One that's perfectly in phase with the strain, it goes like sine omega t, and another one goes like cosine omega t. That's perfectly in phase with the strain rate, right? And so this one is a dissipative part, and this one is a stored energy part, and hence we call G prime the storage modulus and G double prime the loss modulus. So you can think of that equation as kind of definitions of G prime and G double prime. And of course, in reality, we measure G star and phase angle, so we can calculate G prime as G star times cosine of delta, and G double prime as G star times sine delta. In practice, the computer running the rheometer is going to make all those calculations for you, but sometimes it's useful to understand what it's actually doing, because sometimes you get squirrely data, and you can start thinking about, well, why is it so strange? And I usually go back to looking at the phase angle and seeing whether I actually believe that it did that calculation right with an oscilloscope. Okay, so we can also get the storage and loss moduli from the simple Maxwell model, which again just had one relaxation time. It works out to be perfectly simple. To do this, you have to do integration by parts twice. I don't have time for all that today, but we get very simple relations for both storage modulus and loss modulus, and they look like this. So here I'm normalizing by the Maxwell modulus so that this value of G prime at high frequencies or short times is the Plateau modulus, GM, right? And so there's simple limits for these things. If I think about the low frequency limit, then I can basically throw away this thing and keep the 1, right? That goes like omega squared. G prime goes like omega squared. G double prime goes like omega. So slope of 1 for G double prime and slope of 2 for G prime. We see that for any viscoelastic liquid. If we can get to low enough frequencies that are lower than the reciprocal of the longest time. So for nice monodispersed materials, they almost look like this Maxwell model. We'll see it's not quite that, but it's close. Whereas for polydispersed polyethylene or polypropylene, you'll never see the slope of 2. You might get lucky and see the slope of 1, but the slope of 2, you'd have to go to 10 to the minus 5 radians per second or something, and that's just not practical, right? So, and then at the high frequency limit, which I think is one more click, what do? For high frequency, we throw away the 1 in each of these denominators. This one just goes to GM, so it's nice and flat. And this one goes to 1 over frequency, basically, so it has a nice slope of minus 1. In practice, with polymer melts, you never see slope of minus 1. It's typically something like minus 0.3 or something like this, even for monodispersed materials. So that tells us that our cheap and cheerful Maxwell model doesn't strictly apply to polymer melts. And then quite generally, 2 important relations at the bottom. We can get, since it's linear viscoelasticity, all information is gotten from every experiment. So the zero shear viscosity can be determined from the ratio of loss modulus and frequency at low frequencies. And the steady state compliance can be determined from this relation here. So at least for monodispersed materials, that's easy. The Maxwell model does apply to some things. So it happens to apply to worm-like micelles. So that's a nice example of a complex fluid that's very viscoelastic. And you can see it really does have a very flat G prime at high frequencies. And G double prime, at least for a while, has this nice minus 1 slope. So it really looks quite like the Maxwell model. Whereas for monodispersed polymers, it's not quite so simple. I think this is, again, a linear polybutadiene melt. And G prime is not quite perfectly flat at high frequencies, although we're approaching the plateau modulus of this material. It's getting pretty flat. It gets flatter and flatter as G double prime becomes lower and lower compared to G prime. That's all about the phase angle getting closer and closer to 0. But for even monodispersed materials, about the steepest slope one ever sees is about minus 0.3. So that just tells you there's some relaxation times in this rubbery plateau that we would need to account for in some sort of model. I think Professor McLeish will tell us about that a little bit tomorrow. So, right, so here we see a more complete spectrum. The previous data were just isothermal data, but now I'm taking data at a lot of different temperatures, including temperatures that are very close to the glass transition, and making what's called a master curve by time temperature superposition. But you can see it's oscillatory shear can be very, very powerful, because at least I can pretend that, at 25 degrees, if I had a rheometer that could go to 10 to the 10 radians per second, good luck with that, maybe I'd see the glassy modulus, right? So here's the glassy modulus, G prime being flat at high frequencies. Here's the plateau modulus, G prime being flat at intermediate frequencies now, that were the highest frequencies in the previous experimental data that we showed. There's kind of a transition zone in between the two, and then we have the rubbery plateau and eventually terminal response with G double prime proportional to frequency and G prime proportional to frequency squared. So the loss modulus is telling us how much energy is getting dissipated. So there's a big dissipation in the vicinity of the glass transition when monomers just start to move. And then there's another big dissipation at low frequencies where the whole chains are now starting to relax. So a nice way to look at that is with loss modulus on a linear scale. These are binary blends of polybutadienes. And as I have more and more of the high molecular weight component of my blend, this low frequency peak is rising. It's telling you that more and more of the stress is getting dissipated by those long chains as I have more long chains. And of course, at the same time, I have less short chains. So the peak at high frequencies where the short chains are relaxing is dropping. And the curves Michael's very proud of, because this is kind of almost state of the art of what molecular models can do, in that since this is a comparison on a linear scale, it's actually pretty good theory that I won't have time to tell you about. But a lot of oscillatory shear is just about pattern recognition. You know, that you see a shape of G prime and G double prime and you say, okay, that looks like whatever. So this one is our, the filled symbols are again our monodisperse linear polymer, right? Nice flat plateau. And then for a 3-arm star polybutadiene, we picked one that has similar viscosity. So it's not quite exactly the same, right? It has maybe a factor of 2 difference in viscosity, but they're pretty close. G double prime is almost the same at low frequencies. But you can see the star polymer doesn't show this entanglement plateau character. It does have a plateau modulus, and the plateau modulus is the same as the linear polymer, but it has relaxations all through the what we would call the rubbery plateau of the linear polymer, because it has many ends that are retracting and dissipating energy, basically. Yes? So anytime we see A sub t, it means it's a master curve. We took isothermal data at a number of different temperatures and patched them all together to make this master curve. Yeah. In the previous slide, it's the same. It's a. Oh.
Before that. Yeah. So the data was obtained from, like you said, like from time temperature.
Yep. All of them typically are going from something like 10 to the minus 3 to 10 to the 2 radians per second. And those are actually these data for the data at 25 degrees, which is my reference temperature. And then I have lower and lower and lower and lower and lower temperatures, and these data are at something like minus 99 for the lowest temperature data. And then we slide them along the frequency scale, that's the A sub t, to...
It's like if we are going to lower temperature, we are looking for dynamics which are at higher frequency.
Yep, effectively, yep.
Hi. I had a question. When you go to higher frequencies, why? I mean, I understand that at the entanglement region you have your G dash above G double prime, but then when we go to the end of the thing, why does it switch again to the glassy modulus being higher than the G dash being higher than the...
Right, so eventually we're entering the glass, right? The glassy state is a solid with G prime much bigger than G double prime, and it will be really flat. I didn't get to quite low enough temperatures to show that it's really, really flat here, right? But it will be. G double prime will keep going down, basically. But in this transition zone, we're relaxing significant amounts of the stress, something like a drop of 1,000 in stress, right? And so what does that tell you? It says only 1 part in 1,000 of the stress is actually still there at longer times or lower frequencies, right? So we've relaxed a heck of a lot of the stress just by segmental motion of the polymer, local motions of the polymer. So stress is all about orientation, remembering the orientation of chains, and a lot of that's gone by the time we get to the rubbery plateau. Yeah.
So at that end, you're basically probing these really small segments of the chain? Or...
Yep.
Yeah. Okay.
Yeah. Yep. So back here, it's too fast and nobody gets to move. Then monomers start moving, and as more and more monomers, we get all the way to what's called the Rouse time of an entanglement strand, and all that stuff gets to relax, basically. Yep. Great question. Okay, and then this is just the penultimate example, is comparing a linear polybutadiene with a 6-arm star polybutadiene in this case that has the same span molecular weight. So in other words, the molecular weight of the linear polymer is almost twice the molecular weight of one of the arms, which is the span across the molecule. And that means all this high frequency stuff's the same. But now, of course, the linear polymer is relaxing here. The star has a much delayed relaxation time because it has to retract its arms instead of the faster process of reptation. And then the star has all this lovely viscoelastic character that we sort of saw in one of the previous slides as well. Then my last oscillatory shear pattern matching has to do with networks. So here we compare a nearly perfect network where we're end-linking polydimethylsiloxane, and the nearly perfect network has G prime almost independent of frequency, and G double prime, of course, very, very low. Those two statements go hand in hand, right? If G double prime is way below G prime, it means the phase angle is almost zero. And that's why the data get noisy at the end. I can't resolve the phase angle anymore with enough precision. So you can never get G double prime, 4 orders of magnitude below G prime because you can't resolve the phase angle that close to zero. And then we made intentionally imperfect networks by comparing telechylic or mixing two types of telechylic PDMS, one with 2 reactive end groups like we use for the perfect network, and one with only 1 reactive end group. So we intentionally introduced what are called dangling ends in the network. And then, of course, that lowers the Plateau modulus, but also makes G prime not quite flat. It's approaching flat at the lowest frequencies. And G double prime is down here. It's much closer to G prime in this case. It means the phase angle is easily measured and maybe 1 degree or something like this. Questions? I want to shift gears at the moment. Yes, one more question? Yeah.
When you do a rheology experiment, is it stress control or strain control?
That's a great question. Some rheometers are stress controlled. Some rheometers are strain controlled. And if you talk to the people selling the rheometer, they'll say it doesn't make any difference because I can emulate the other one with mine. So I can do each of them can do both. That is complete nonsense. But this is these guys trying to sell you something that costs way too much money. Even my new BMW car doesn't cost as much as these guys. But it's a great question. If we want to do a creep experiment, it's better to do that in a stress control rheometer, right? It's only marginally better because now fast feedback can actually, in the controlled strain rheometer, can actually emulate creep okay. It can keep the stress constant pretty easily. The tricky part is we didn't talk about recovery, but the best way to measure the steady state compliance is in the recovery experiment where we set the stress equal to 0. That you need a controlled stress rheometer to even think about doing. So that's where you really need it. Whereas oscillatory shear, it doesn't matter. I talked about applying a sinusoidal strain, but you could apply a sinusoidal stress. It doesn't really make any difference operationally. As long as the fluid is resistant enough, I should say. If you put a really light fluid in there, then you'll get inertial effects in the controlled stress rheometer. Yeah.
It would change whether the stress was strain led in the space.
No, the stress always leads the strain. The whole story looks exactly the same, actually. Yep.
Maybe I don't understand that.
Okay, we can talk about it after. Yeah. Yes.
Yeah, so in all these calculations that you have shown till now, you have assumed a Maxwell model.
Well, I mean, the Maxwell model we have in the back of our mind is a simple way of thinking about things, right? But we saw that it doesn't really apply to polymer melts, for instance, right? They're a little more complicated than that. And there are reptation and tube-based models that do a much better job, but they're harder. Yeah. And I don't have time to tell you about those models so much, yeah. Yeah. But it's pretty close for a monodispersed linear polymer. It's pretty close to Maxwell model. Not too bad.
Yeah, so the results will be qualitatively same. Can you comment on that? The results will be qualitatively same for the other models as well, like maybe Kelvin Voigt or similar linear current models.
Oh, I don't want to talk about all those models. But Tom McLeish will tell you about tube-based models that do a really nice job. We sort of saw the curves in the binary blend data that were pretty close to the data, right? So yeah, that's kind of state of the art. Yeah. But other simple models, I think, are not so useful, whereas Maxwell is probably the best choice for monodisperse polymer melts. Yeah. Okay. So now I want to shift gears a little bit, and we've learned a lot about random walks. Well, random walks apply to dynamics as well. So if we think about a colloidal particle moving around in water, what happens? It gets little kicks from the solvent in random directions and gets a Brownian motion. This is exactly what Professor Brown studied in his microscope long ago, watching things move about. In fact, I think he thought it meant they were alive or something at the time, but that turned out, of course, most colloids are not alive as far as I know. But they move around as though maybe they were alive, and so the path they take, of course, is different for every particle, and because it's just a random walk. And so the mean squared displacement of the particle is actually diffusive almost right away. As soon as it's moved a distance of order of its own size, the motion is diffusive, and it means the mean squared displacement is in dimensions is 6 times the diffusion coefficient times time. So it's just linear in time. And that introduces what we call the diffusion coefficient, and we could measure that by watching the particles move around. Let's see. So more generally, the same sort of law applies for how far in space things have moved. We use our diffusion coefficient in this way to estimate how the mean squared distance that something's going to move in a certain amount of time. Now I want to tell you about what Einstein did in his PhD work. And so there's a related experiment that if we can apply a force to the same colloidal particle, what happens? We apply a force, it pulls the particle in this direction. The particle almost instantaneously adopts a constant velocity because the viscous resistance of the solvent is applying an equal and opposite force on that particle right away. So we get what's called terminal velocity. And so operationally, you might think about, well, I have a charged particle and I put it in an electric field, apply an electric field to it to apply the force, for instance. And then we have what's called the friction coefficient, which is the ratio of these two vectors. The force vector and the velocity vector are both pointing in the same direction. Their ratio defines the friction coefficient. And what Einstein did, so both of these experiments were being done in the late 1800s, and what Einstein did in 1905 is connect the two in kind of the language of the fluctuation dissipation theorem. His dissertation in English is something like a new determination of molecular dimensions, and he recognized that these two coefficients are actually related in a very easy way, known as the Einstein relation. The diffusion coefficient is thermal energy kT divided by friction coefficient. So that's nice. I think intuitively, if the friction coefficient is large, it means the thing is going to diffuse rather slowly, right? So that's in a sense what the blue relation is all about. So now I'm going to put all the important stuff of that up at the top of this one. And at that time, Stokes had already solved the complicated fluid mechanics problem of flow past a sphere, very elegant solution. And he determined that the friction coefficient of the sphere is 6 pi times the viscosity of the surrounding medium times the radius of the sphere. And that we can combine with our Einstein relation to get what's called the Stokes-Einstein relation. We put our friction coefficient in there, and it's now kT over 6 pi a to r, which we can turn around to get what's called the hydrodynamic radius, solving for R, basically. Because there's lots of ways to measure diffusion, right? We can measure diffusion by NMR, we can measure diffusion by dynamic light scattering, lots of different methods. And it's important that we can apply those methods to polymers, we can apply them to complicated colloids that are not spheres, all kinds of things. And what this thing is going to do is give you the effective radius of a sphere that has the same diffusion coefficient of whatever you're measuring, right? So that's what we call it, hydrodynamic radius. And for polymers, that radius is never very different than the radius of gyration, so it's kind of a useful thing. Okay, now what I want to do is build our first model of polymer viscoelasticity, known as the Rouse model. So what we have to do is we're going to map the configuration of our chain onto a system of beads connected by elastic springs. All the springs have the same spring constant. Each bead has the same friction coefficient. And so the beads are kind of the center of viscous resistance, and the elasticity is coming from the springs. And I'm not going to solve that problem. Rouse solved it. It's a beautiful, if I have n springs and n plus 1 beads, I've got an n plus 1 differential equations that are coupled. Coupled harmonic oscillators is one of the few problems that physicists can actually solve. And so he had fun solving that in a beautiful, elegant way. I'm not going to tell you about that. I'm going to tell you the cheap and cheerful scaling because we don't have time for all that solution. And the cheap and cheerful scaling is easy because each bead has friction zeta, and there's n beads, so the chain's friction is just n times zeta. And then I can use my Einstein relation to know the diffusion coefficient predicted by the Rouse model right away, just kT over n zeta. So that's kind of, we didn't do any work for that, right? And it's the diffusion coefficient is going to get slower and slower as I go to larger and larger chains. So each chain diffuses a distance of order of its own size in its Rouse time. So that means I can estimate the Rouse time now as just R squared over D. And then that's just friction over kT times n R squared. So that n R squared is kind of a general result for the Rouse model. It turns out for linear polymers, the Rouse model only seems to apply when we're in theta solvent, or we're in a situation of a polymer melt where in both cases the chain is ideal. So R is Bn to the 1/2, or R squared in this case is B squared times N, and then we get N squared for our relaxation time. And here we recognize that the monomer time, which is the shortest time in the Rouse model, is tau 0. That's basically zeta b squared over kT. And in solution, we can write that one as essentially solvent viscosity times b cubed over kT, because the friction coefficient of individual beads is just like the individual spheres, right? I dropped the 6 pi, but otherwise it looks essentially like that, has that character. So at the level of scaling, we don't keep any of those prefactors. And of course, Rouse had never heard of the word scaling. He was a mathematician. He did the full elegant solution of these coupled harmonic oscillators, which is beautifully described in a number of books actually now. And of course, he gets the prefactor. So he gets a prefactor. Actually, our prefactor is alarmingly large. It's 6 pi squared, but no matter. He definitely did it right. But all of the scaling character, like going like n squared, for instance, still survives, and those are the things we're most concerned with here. Then for any of the unentangled models, so we're going to talk about a second one in a moment, the Zim model, they always have the terminal modulus to be kT per chain. So that's C over N is number density of chains times the thermal energy kT. So really, I have to integrate G of T to get the zero shear viscosity, but it's controlled by the upper limit of the integration, And so it's roughly, with dropping prefactors, just the product of this terminal modulus and the Rouse terminal time. And so this one went like 1 over n, and that one went like n squared. So now the viscosity is predicted to be proportional to chain length. So now we can also have another model that looks quite like the Rouse model. It would be that same beads and springs picture, but instead of the polymer moving without really interacting with its environment other than through the solvent viscosity resistance of each bead's motion, the whole polymer could move together and be hydrodynamically coupled. Then it looks a lot more like the sphere that we started with, right? It's the Zim diffusion coefficient is kT over eta SR, right? This is, maybe this, we want to put 6 pi in this also, but let's not go there. And this one applies to both good solvents and theta solvents, so we'll keep it with the Flory exponent nu, right? So it's quite general that R is B times N to the nu. And really, when Zim presented his model, he had a crossover from pure Rouse to pure Zim. There's a parameter in there, and we're kind of focusing on the strongly hydrodynamically coupled limit. But we'll see that that's a bit of a mistake when we get to comparing with data. So let's see. So we can do the same trick. Each chain diffuses a distance of order of its own size in what's called the Zim time. Tau z is r squared over dz. And we can compare those two right away. So that goes like r cubed, which is n to the 3 nu, right? So, and it's the same tau 0, the fastest time, the time scale of motion of monomers is the same in the two models. And of course, Zim did a really elegant calculation, even in some sense, I would say less elegant than Rouse, because Rouse did it exactly. Zim had to pre-average the Oseen tensor and all these things. I think he knew the answer, so he got these coefficients very close. I honestly don't understand how he got these coefficients so close to experimental data. But anyway, he gets the coefficients, and it doesn't look too different than our cheap and cheerful scaling version, but we wind up with this 0.163. Out in front when things are done properly. And then we have the same trick with the terminal modulus being kT per chain, and we approximate our integration, again, as just the product of terminal modulus and terminal time, and that works out to be r cubed divided by n. So that lets us get the intrinsic viscosity, which is nice. So intrinsic viscosity, unfortunately, was developed by chemists that like crazy units. So intrinsic viscosity is going to have units of the reciprocal of whatever concentration I used. But it's basically what's known as specific viscosity, viscosity minus solvent viscosity divided by solvent viscosity, divided by concentration, right? And so if you think about that, that's perfect. We're going to divide by these two guys, and we're left with r cubed over n. And that's kind of the basis of what's known as the Fox-Flory relation, really derived from the Zim model, that the intrinsic viscosity is r cubed divided by molecular weight. And this is a constant that's supposed to be universal. It's actually 0.425 times Avogadro's number, if you're really interested. And Lou Fetters has a great review that kind of shows that's not a crazy number at all, actually. It looks like for a lot of systems that's pretty good. So it's the Zim model that seems to apply for the intrinsic viscosity of flexible polymers. Here shown for polystyrene in 3 different solvents. So this one is a theta solvent with nice slope of a half. Nu is equal to a half. So 3 nu minus 1 is also equal to a half. And I think something got cut off here, but there's 2 cases. This is the theta solvent case, and this is the good solvent case. And so in good solvent, nu is equal to 3/5 or maybe 0.588, and you get something like 0.76, and that seems like it works. And then there's an intermediate case, which has excluded volume. and it's roughly half the excluded volume of polystyrene and toluene. It has the 0.76 character at high enough molecular weight, but then at low enough molecular weight, unfortunately there's only one point in this data set, but I think there are better ones in the literature. You can actually see the slope of a half. Of course, those data should never go below the theta line anyway, right? And that's the crossover that was the thermal blob that was talked about this morning by Shura. And this is kind of a molecular weight, well, where this 0.76 hits a half, maybe back here, is the molecular weight of chain that is in the thermal blob. So that's kind of a good way to experimentally maybe determine the thermal blob size for a given solvent. So this one nicely compares Rouse and Zim. So Rouse makes a much simpler prediction. The intrinsic viscosity is proportional to chain length. Too bad for Mr. Rouse, it doesn't really work. And so Zim seems like it works better, right? So we're comparing it with slopes of 1 and 0.76. It's clear that the data for flexible polymers support the Zim model. And I'm only showing you a tiny subset of all the millions of data sets that do support that. However, my group is now really interested in much more rigid things. And it looks to me that cellulose, from these data from Professor Mark, so the intrinsic viscosity molecular weight relation is known as the Mark-Huink relation, and that's the Mark. And he says for cellulose, no, the exponent is more like 1, and it's exactly what is expected by the Rouse model. So maybe when the chain gets stiff enough, then it's not so easy to drag all the solvent with it, right? Now it becomes more free draining and the solvent can move through the coil. That's just Professor Colby's speculation. Now I want to talk about Rouse modes. Right. So the idea of Rouse modes is that we have, well, even in the Rouse model, we have this mode index. P runs from 1 to n. The key point being the fastest one is p equal to n, and the slowest one is p equal to 1. So that's maybe a little bit confusing. And the basic idea to think about the physics of the Rouse model is to say that each mode is going to relax sections of the chain that have n over p monomers. So what are we going to do with that? Well, we have a terminal time and a terminal modulus, and we are going to replace the n's in these things with n over p to get the relaxation times and moduli of each mode. So that's done like this. So this one had n squared, I replace it with n over p squared, and I solve for p. And then I put that into this one, which is also going to have n over p, right? And then I wind up concluding that the modulus should go like t to the minus 1/2 in the Rouse model. And that's, of course, a known result for the Rouse model as well. And all we need to do is multiply that simple power law with an exponential cutoff at the longest time, which is tau r. And then we have a full g of t prediction of the Rouse model. Well, this is kind of the cheap and cheerful scaling version of the Rouse model. We can compare that with Rouse's solution. So Rouse solved the many coupled harmonic oscillators and got a sum solution, which is in blue. And our cheap and cheerful one is shown as the red dots. So you can see they seem to agree reasonably well. And the nice advantage of the cheap and cheerful one is it's telling you the assumption we made that each mode is relaxing sections of n over p monomers is maybe the right way to think about what the Rouse model means. So it turns out the Rouse model actually applies whenever we don't have entanglement effects in polymer dynamics and we're not in dilute solution. So what does that mean? Well, there's a semi-dilute solution that could have a region that's unentangled. And for polyelectrolytes, that region is surprisingly wide concentration range so that we can test the Rouse model. The Rouse model predictions, when plotted in this format, are just these curves. There's nothing we can do about those, and all we can do is put our data on there to compare. These are actually Eric Amos's data. And you can see it works reasonably well. So maybe the Rouse model actually does work for something. We tried to do the same thing with low molecular weight polystyrenes that are not entangled. I have to say, the entanglement molecular weight is something like 18,000. So this one is kind of barely entangled, the small circles. But as you go to longer and longer chains, you can get further out here and maybe have the slope of a half. So that's kind of the best we can do at present. So we can do the same trick with the Zim model. So again, it's the same mode indices, and p equals 1 is the slowest mode, and p equal to n is the fastest motion of the individual monomers. Each relaxation mode is going to relax sections of the chain with n over p monomers. So whenever we see n, we're going to put in n over p. And so we do the same trick. We do it first for the relaxation time. We solve for p, and we get this. And then we have also n over p for the modulus, and we put this p into there to get this one. And now we have a different exponent of minus 1 over 3 nu. And so that has different values for theta solvent and good solvent. And then we do the same exponential cutoff trick that at the longest relaxation time, there are no more modes, so we're just going to have it exponentially relax. And here you get the two exponents. In theta solvent, the exponent should be 2/3, which is quite different than a half. And in good solvent, it's 0.57, which is maybe closer to a half, but still different. And at least in theta solvent, the Zim model seems like it works nicely. So these are old data from John Ferry's group that beautifully have, again, the Zim predictions in this format are just the curves. There's nothing we can do about those. And the best you can do is put your data on there. It looks like it works. It looks like it works reasonably well. So maybe in theta solvent, the Zim model applies. In good solvent, it doesn't seem like it applies so well. So I mentioned that Zim really had a way to cross all the way from fully hydrodynamically coupled to kind of marginally hydrodynamically coupled. And these guys look like they're getting closer to the Rouse model, because the Rouse model would have G prime on top of G double prime with a slope of a half, right? So it's not quite the prediction of Mr. Zim. So one way maybe to think about why it's Zim instead of Rouse is this mean squared displacement of monomers. So those are predicted by the Rouse and Zim models as well. We get subdiffusive behavior on short time scales up to the coil size, right? And then once we get to the coil size, things start actually diffusing with a slope of 1 in each case. But you can see each mode is going to be faster in the Zim model. In other words, it gets further in the Zim model than it gets in the Rouse model. And maybe that's why Zim wins in dilute solution. It's a faster way to success. Okay, so quick summary. We had a Maxwell model. It just has one relaxation time. It works for some things, but it isn't usually thought to be particularly precise, but at least has the virtue of being simple. Boltzmann superposition works only for linear viscoelastic response, but for instance, we can get the zero shear viscosity from the time integral of g of t. We could also get it from oscillatory shear from the low frequency character of the loss modulus. Okay, and then the Rouse model seems to apply to polymers that don't have entanglement effects but are not dilute solutions. While the Zim model seems like it applies in dilute solution, at least perfectly maybe for theta solvents, and now when we get to good solvents, maybe the coil is expanding enough that we get a little bit of what's called free draining character, that not all the solvent inside the coil just moves along with the polymer. So, but it gives us this very important Fox-Flory relation. And then I'd like to conclude with a very simple example of what you might use the Fox-Flory relation for. You can calculate the intrinsic viscosity. So these are for what are called starburst dendrimers. There's a nice example of a starburst dendrimer at generation 3 over there. You can imagine by the time you get out to generations of 7 or 8 or 9, things get really crowded on the surface, right? And so the intrinsic viscosity of dendrimers, actually as a function of generation number, always shows a maximum. And the reason we can think that through in the Fox-Flory relation, at the beginning, for small generation numbers, the size is increasing faster than the mass, right? So in other words, the volume of the thing, r cubed, is increasing faster than the molecular weight. Whereas later on, I'm adding so much junk to the perimeter, but I'm not increasing the volume that much. The molecular weight starts increasing faster than the volume, and that brings this thing back down. So that's kind of an interesting homework problem from, I think, chapter 8 of my book with Professor Rubenstein. Do we have any questions? Yes?
How should we think about like the friction in a melt, like the dissipation in a melt, when there is no solvent?
Well, that's a great question. So, we can't relate it to solvent viscosity. There's no solvent, right? But there's always still some frictional resistance, because that friction coefficient is essentially the monomer time, the time scale for individual monomer motion in different units, right? So there's always some time scale. I think the tau zero maybe has, for me, a little more physical meaning than friction in this case, right? But yeah, but the two are the same thing. It's just they have different units. Wow, it was either clear as anything, probably not. I apologize that I really gave you guys what I give in 3 75-minute lectures in one lecture. Tom, Sir Tom. Sure. Let's think that through on the fly. So the Rouse model for those branched objects, the relaxation time should be proportional to n times r squared, the size squared, right? So as I put more and more branches at the same n, I'm making a smaller size, basically, right? So those are typically going to, at the same n, have a shorter relaxation time than the linear polymer with the same n, right? And let's see, if we think about the Zim model, the thing is just r cubed, right? And so at the same n, r, as I put more and more branches, r is going to get smaller, 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 and it's going to relax faster. I think that's right. Yeah, the mode structure changes a bit because I think with the Rouse, the longest mode you can have is kind of the span molecular weight, right? So yeah, so it does change a bit, but the longest relaxation time for sure gets smaller, and the viscosity gets a bit smaller. Yeah. Yeah.
Is it really true that for this branched object, the longest relaxation time is the time to diffuse your own size? Is it not true that for densely branched objects, Newtonian relaxation will be slower?
Well, you have in mind, I think, entangled branch polymers maybe, but for sure entangled branch polymers, what you're saying is correct. But I think for unentangled, it it shouldn't matter, right? Rouse model is just a single chain model. Yeah.
You are saying the same thing as me in different language. You say unentangled if it's not branched enough.
Yeah, okay. Yeah. Okay. Other questions? We have lots of time. Oh, Michael's shaking his head. That's always a good sign.
Parallel branch and unentangled.
Yes.
So the Rouse model is spherical beads with a string between them.
Yep.
I was
And ignoring all environment around. Yeah.
ignoring the solvent as well.
Well, so the solvent viscosity shows up in the friction of each of the individual beads. But yeah.
I'm surprised that it works so well at all because you're assuming spherical beads.
Oh yeah.
Where solvent doesn't really look like that.
No, that's true, but an individual, well, what we would call monomer would even be bigger than a chemical monomer, maybe a Kuhn monomer. It's some elongated thingy, not a sphere, but it still has a certain friction, and each Kuhn monomer has essentially the same friction, right? So it's just, yeah, it changes what we call friction. So, but you notice I didn't put 6 pi in there, right? So I'm not really taking it that seriously. Yeah. Sure. You got a question as well?
Maybe it's spoiler, but will we get to the transition between Rouse model to Rouse and rotation to the frequent diffusion thingy? Will we get to that in the next lecture? Or?
I hope so, but I'm not giving that lecture. But I believe Professor McLeish will tell us about maybe the crossover from Rouse to reptation at tau e and all that. Yeah. It's coming. It's a great question because it's near and dear to our hearts. Yeah. Yes.
Yes, you said repetition 3 times, and I don't know what that is. Can you explain what repetition is?
Well, the real important thing is I forgot to tell you that the Rouse model is kind of the mother of all dynamics models of polymers, right? So it already went into the Zim model. I'm just dragging the solvent with, right? But all those modes are kind of still there, right? But the reptation, the way I think about the reptation model or any tube model is the surrounding chains are preventing Rouse motion in a lateral direction, perpendicular to the axis of the tube, and restricting the Rouse motion to move along the tube. Yep. And Professor McLeish is an expert on explaining exactly that, so I'll leave him. I don't want to steal his thunder. Yes? Yes? You have it? Oh, no. Uh-huh. You're thinking about worm-like micelles. The worm-like micelle data that I showed you are strongly entangled. They're way above their overlap concentration. Below the overlap concentration. That's a great question, and I'm not actually an expert because I worry that as we dilute the worm-like micelle solution, the worms actually get shorter. And I don't actually know if you actually have dilute worms, if you know what I mean. Maybe they're back to almost spherical micelles. I don't. Tom, you might know the answer, but it's a great question. I haven't seen dilute data on worm-like micelles. Is my only worry. You'd think you'd be able to find such, right? Yeah. So sorry, I don't know the answer to this one. Yes?
How will these models will be impacted by Polymer Viscosity?
Oh, that's a lovely question. We understand that very well for the Rouse model, thanks to the work of Professor Ferry. So, we talked about diffusion coefficient, and the n in that is the number average molecular weight. We talked about zero shear viscosity. The n in that is the weight average molecular weight. We also talked about relaxation time. that had n squared. Those ones are mz times mz plus 1. So it's much more complicated, I should say. Yeah, yeah. Great question, though. Yeah. Okay. Thanks so much for your attention. Don't forget to go swimming.